Alright, so here we are looking at Chapter 8 problems. Chapter 8 review problems number 873. What's the frequency in hertz of blue light having a wavelength of 436 nanometers? 436 nanometers, and we're looking for hertz, right? Which is frequency. Well, wavelength times hertz equals the speed of light, and the speed of light equals 3.00 times 10 to the 8th, and that's meters per second. Alright, this is in nanometers, so if we want to convert that to meters, then we have to go 1, 2, 3 is micrometers, 1, 2, 3 is millimeters, and then 1, 2, 3 would be meters, right? So that's 1, 2, 3, 4, 5, 6, 7, 4.36 times 10 to the negative 7 meters. Alright, so that's our wavelength, 4.36 times 10 to the negative 7 meters. And we have to convert it to meters because this is in meters per second. And frequency is in per second, right? And so we're going to solve for this value here, and we're going to use the speed of light there. So we have 3.0 times 10 to the 8th divided by 4.36 times 10 to the minus 7. Alright, so I'm getting 6.88 times 10 to the 14th per second. Alright, so that's our frequency. That's 873. 873. 6.88 times 10 to the 14th. Okay. 875. A certain substance strongly absorbs infrared light a wavelength of 6.85 micrometers. What's the frequency of light in hertz? Alright, 6.85 micrometers. We have to convert that to meters, right? And for every 1,000, that's nanometer, or millimeter, and a million is a micrometer. So 1 million micrometers in 1 meter. And so 6.85 divided by a million. 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6. 6.85 times 10 to the minus 6 meters. So that's our wavelength here. Our frequency is what we're solving for. Again, C is 3.00 times 10 to the 8th meters per second, right? Again, unit analysis, we can do a lot here. We have 3.8, let's see. So we have 6.85 times 10 to the minus 6. So we have 3.0 times 10 to the 8th divided by 6.85 times 10 to the minus 6. And the frequency is 4.38 times 10 to the 13. All right. 4.38 times 10 to the 13. All right. 877. Ozone protects the Earth. This shields a maximum UV light range of 295 nanometers. 295 nanometers, which is the same as 295 times 10 to the minus 9th meters, which is the same as 2.95 times 10 to the minus 7 meters. All right, so that's our wavelength. So if we take our frequency again, wait, what are we asking to solve for 877? What's the frequency? Yeah. So we take our speed of light and divide it by the wavelength here, which is 2.95 times 10 to the minus 7. And I'm getting 1.02 times 10 to the 15. So it's 877. 1.02 times 10 to the 15. Okay. 879. In New York City, the radio station, what's the wavelength? All right, so the 101.1 megahertz. All right, HZ. All right, big H, Z. There we go. 101 megahertz. And again, our wavelength times our frequency equals the speed of light. Speed of light is 3.0 times 10 to the 8th. So we want to identify the wavelength this time. So we take this divided by 101 megahertz is 101.1 megahertz is 101.1 times 10 to the 6th hertz, right? So we can divide this by 101.1 times 10 to the 6th hertz. This is meters per second, and then that'll give us our answer in meters, right? All right, so we have again 3.0 times 10 to the 8th divided by 101.1 times 10 to the 6th. All right, and now I'm getting 2.96 meters. And do they ask us any units specifically? 879 in meters. So I'm getting 2.967 meters. 879. 2.965 they got. They must have used one more digit on their speed of light. Maybe, I'm not sure there. Okay, so close enough. 879, 881. There's been some concern in recent times about the possible hazards to people who live very close to high voltage electricity. Electricity in the wires oscillates at a frequency of 60 hertz, which is the frequency of any electromagnetic radiation that they emit. What is the wavelength of the radiation in meters? What is it in kilometers? Okay, so we're looking for wavelength. We know the frequency is 60 hertz. Right. So we have 63 times 10 to the 8th divided by our 60, and that will give us our wavelength there. Okay, so we have 3 times 10 to the 8th divided by 60, and that'll be in meters, and it looks like it's 5 million meters, which is 5,000 kilometers. 5,000 kilometers or 5 million meters. So 5 times 10 to the 6 meters, 5 times 10 to the 3rd kilometers. All right. So 883. Calculate the energy in joules of a photon of red light having a frequency of 4 times 10 to the 14th hertz. What's the energy of 1 mole of these photons? All right, 4 times 10 to the 14th. 4 times 10 to the 14th, and that's in hertz. Okay? And to find the energy of the photon, we need to know that energy is equal to Planck's constant times frequency. Planck's constant times frequency. All right? And Planck's constant, we don't need to memorize, but we need to be able to remember that it's a constant that relates energy to frequency, right? And where is the energy? Planck's constant. Planck's constant on page 312, 6.626 times 10 to the minus 34. And the units are joules per second. And that's why if you take frequency per second, multiply by this, you're going to end up with joules. Okay, so we have, that's our frequency, multiply it by this value here. So we have 4 times 10 to the 14th times 6.626 times 10 to the minus 34. All right, so the energy is 2.65 times 10 to the minus 19th joules. All right, make sure, what is the energy in, oh, so calculate the energy in joules of a photon. That's one photon. All right. So 883, the first part is 2.7 times 10 to the negative 19 joules. That's right. So now to find out 1 whole mole of these photons, right? So that's just 1 photon. And if we want a whole mole of the photons, we have to multiply that number by 6.02 times 10 to the 23rd. So that is 159,554 joules, or 160 kilojoules about. And this is 883, 160,000 kilojoules, or 160,000 joules. All right, 885. In a spectrum of hydrogen, did we do 883? Yes. In the spectrum of hydrogen, there is a line with a wavelength of 410.3 nanometers. What color is this line? What is its frequency? So if it's 410.3 nanometers, so we're looking at 400 to 700 nanometers. This is our light, range of light, right? The shorter the wavelength, the more dangerous. And we know that beyond our visible wavelength, so this is visible, beyond our visible, the dangerous ones are the ultraviolet, right? So that's the shorter side. Beyond the visible on this side are the infrared. That's not the dangerous ones. So we know that smaller wavelength is higher energy, more dangerous. Therefore, this is our ultraviolet. Violet helps us remember that this is the purple side. So that should be a violet-colored light, or a purple-colored light. In the spectrum of hydrogen, there is a line with a wavelength of 410 nanometers. What's the color of this line? So 885A, violet. All right. What is its frequency? All right, so we want to identify its frequency. Again, wavelength, frequency, speed of light. C equals 3 times 10 to the 8. All right. 3 times 10 to the 8th divided by wavelength in meters, though, and we have it in nanometers, so that's 410.3. So it's 410.3 times 10 to the minus 9th meters. So the frequency is going to be 7.31 times 10 to the 14th. All right, so 85B, 7.3 times 10 to the 14th, yep. And C, what is the energy of each of its photons? So if this is frequency in per seconds, right? And we know that energy equals Planck's constant, which is over here still, times that frequency. So if we take that frequency, multiply it by 6.626 times 10 to the minus 34, that gives us 4.84 times 10 to the minus 19th joules. 4.84 times 10 to the minus 19th. So this was this Planck's constant here. Energy equals 4.84 times 10 to the minus 19th joules. All right, that's 485. 487. Use the Rydberg equation to calculate the wavelength in nanometers at the spectral line of hydrogen, for which N2 equals 6, N1 equals 3. Report your answer using 3 singular figures. Would we expect to see the light corresponding to this spectral line? Explain your answer. Okay, so we're going to use the Rydberg equation. We have to find the Rydberg equation in our book. We don't have to memorize these long equations. But what we're trying to do here is to recognize that there's an equation that can relate, again, the wavelengths of all the spectral lines of hydrogen. All right. So let's write this Rydberg equation on the board here. All right, so are we on 885 still, or? Yeah, 885. All right, so we have the Rydberg equation. 1 over the wavelength equals the Rydberg's constant, 1 over N2 minus 1 over N squared, N1 squared and N2 squared. All right, so here is our Rydberg equation. All right, the Rydberg constant is 109,678. And that's per centimeters. All right, so that's the Rydberg constant there. Our N2 and 1 value is what? Oh, sorry, this is not 85 now, this is 87. Our N1 value is 3, and our N2 value is 6. So N1 value is 3, so 1 over 3 squared, which is 9, minus 1 over 6 squared, 36. 36. So, what is the wavelength of the light? We have to solve for this wavelength value here, right? 109,678. Times 1/9 minus 1/36. All right, so let me see. Are we getting that right there? No, something happened here. What happened wrong? Getting a negative number, and 1/9 minus 1/36 should not be a negative number. So let's try that again. 1 over 9 minus 1 over 36. Okay, so this is 0.08333. Multiply that number by 109,678. And that number times, so I'm getting 1 over the wavelength equals 9139. So this is per meter, right? Or per centimeter, we're in centimeters. Per centimeter. Okay, so we need to invert that number, which I haven't done in a long time on this calculator. Where is it? Well, I can just raise that number to the -1. So looking at 1.09 times 10 to the -4th, and that is centimeters. Now they ask us a question whether or not we can see that light. We know 400 to 700 nanometers is our range, so let's convert this to nanometers, right? There's 100 centimeters for 1 meter, and there's a billion. For 1 meter, there's a billion, or 1 times 10 to the 9th nanometers. So that'll convert that number to nanometers. So we have this value here, divided by 100, times 1 times 10 to the 9th. So 1,094 nanometers. So that's out of our range. It's in the IR, infrared region, right? So the answer is no. What is the energy of the photon? No. Would we be expected to see it? No, it's too long of a wavelength. It's in the IR region. So that's 887 we're looking at now. We would not expect to see this light since it is not in the visible region. Let's see what they weigh at 1,094. Good. Okay.